In this video, we're diving into imaginary numbers, and I'll show you the exact process to solve the problems involving them. You might be looking at the thumbnail and be thinking, I to the 67th power, what even is I? Why did math decide to throw in another letter and make things even more confusing? Stick around and we will break it all down. So what is I? Despite the name imaginary, these numbers aren't made up. They're real tools used in electrical engineering, quantum mechanics, and signal processing. I is the square root of -1. Think of it as a placeholder, just like a regular variable, but with a few special rules that we'll cover. And I've spent hours poring over these concepts and questions to teach you in both a quick and efficient way. Let's build on this concept. So we know that I, or you could write it as I to the first, is equal to the square root of -1. And so I'm going to write this up here because I to the first is equal to the square root of -1. And we'll just leave that here. Now I want to ask you, what is, because we're jumping into the special rules here, what is I squared? Well, I squared is the square root of -1 times the square root of -1. So I want to ask you a few questions. What is the square root of 4 times the square root of 4? You might be thinking, you might know it off the top of your head, but I know the square root of 4 is 2, the square root of 4 is 2, and I can multiply 2 times 2 to give me 4. Therefore, I know that the square root of 4 is times the square root of 4 is 4. So now I want to ask you, what is the square root of 17 times the square root of 17? Well, that should be 17. So when I ask you, what is the square root of -1 times the square root of -1, that should be, you guessed it, -1. So I know for certain that I squared is equal to -1. Right? And from here we can move on to the next one, is I cubed. Now, I cubed, if we know our power rules, we can split that up into I squared times I to the first, right? Now, what is I squared? We just figured that out. That's -1. So -1 times I to the first is just I, or the square root of -1. What does that mean? Well, I to the third is just -I. Are you following? I to the fourth. Now, I to the fourth, we could split that up into I to the third and 1, but it might make a little bit more sense if we split it up into I squared times I squared, because what is I squared? Well, I squared is -1. And what is -1 times -1? It's 1. So, with that, we have a full set. This is kind of the set that you need to know when it comes to complex numbers, and I'll prove to you why. We need to figure out what is I to the 5th, I to the 6th, to the 7th, and to the 8th. And when we do that, it'll make sense why all you need to know is these 4 right here of I to the first, second, and third, and fourth. And if you know all of those, you can do pretty much all I problems with a lot of confidence. So I to the 5th, we can split this up using our power rules into I to the 4th times I to the first. And what is I to the 4th again? 1. And 1 times I to the first is just I. So we have this here. We can split I to the 6th into I to the 4th times I squared. I to the 4th, it's 1. And what is I squared? -1. So I know that it is -1. Right here, I to the 7th can be split into I to the 4th times I to the 3rd. I to the 4th is 1. And I to the 3rd, what is I to the 3rd? That should be -I. So I to the 7th is equal to I. And then I to the 8th is I to the 4th times I to the 4th. That's 1 times 1, and I hope you know what that is. That is just 1. So if you haven't noticed by now, let's look at this pattern. I to the 5th is I to the 1st is I to the 6th is -1. I squared is -1. I to the 7th is -I. I to the 3rd is -I. I to the 8th is -I. and I to the fourth is just 1. So with each one of these, we can split this up and just it's circular, I guess you could say. And you can figure out by dividing whatever number it may be. If it's I to the 303rd, we can divide that number by 4 and we can find what number this is actually equal to. So let's look at our original problem, I to the 67th. I to the 67th, we have to take 67 and divide it by 4. Well, 1 can go into 6 one time, or 4 can go into 6 one time, and I'm left with 2, 7, drop our 7 there. 4 goes into 27, should be 6 times. 4 times 6 is 24. We're left with 3. Our remainder is 3. So this should be I to the 4th raised to the 16th times I to the 3rd. That's how we can split up I to the 67th. And I to the 4th is just 1. 1 to the 16th is just 1. And we're left with just I to the 3rd. Now, what is I to the 3rd? Maybe you remember, it's just negative I. So, I to the 67 is just negative I. And there you have it. Let's look at this other type of problem, because it's not just simplifying I to a certain power, but instead it's putting it into equations, putting them into expressions, and solving from there. We're going to look at several expressions. So, the square root of negative 32, you might know how to simplify a square root. You might have several different ways too, but the way I'm going to go about it is I'm going to try to break it down into things that we know we can simplify and then not simplify. So I know that I can take out this negative 1 and I can make it an I. I know that out of 32, you can multiply 16 and 2. 16 is a perfect square that multiplies to get 32, and I can simplify that to get 4, and square root of 2 has no friends. So I'm left with I, 4, and the square root of 2, and I can simplify this into 4I times the square root of 2. And this is the correct way to write it. You write the I after the coefficient, just like if you had to write 4x square root of 2. Same thing. You treat it just like a variable. So this is how you would simplify an imaginary number under a radical. So we have some operations of imaginary numbers. Here we're going to just do subtraction of binomials. Remember, you're just going to treat it just like you would an x. So if you know how to do this when it's an x, it's the same thing. So we're going to be left with negative 3 plus 4i, or minus 4i when we distribute here. And I'm left with 7 plus 9i minus 3. So 7 minus 3 should give me 4. 9 minus 4. 9i minus 4i should give me plus 5i. And that's all there is to it. Since it's just I to the first here, you don't have to worry about simplifying anything. But we will have to worry about it in this next problem. We're going to FOIL two binomials. Now, when you FOIL, you have to do first, outer, inner, last. When we multiply this 3 plus 2i times the quantity of 4 plus 5i, we take 3 times 4. 3 times 4 will give me 12. 3 times 5i will give me plus 15i. And then 2i times 4 plus 8i. 2i times 5i. Ooh, we'll just treat it like we do with variables. And we're left with 2 times 5, which is 10, and I times I, which is I squared. So, wait, what was I squared again? I squared is negative 1. So what's negative 1 times 10? Should be negative 10. So I just have 12 plus 15i plus 8i is equal to 10. And when I combine like terms, I'm left with 2 plus 23i. And so, just so you know, the proper way to write this and to write your answers is in the form of a plus bi. A plus bi, where your I term, your imaginary term, is second. Moving on, this is common on the ACT. This kind of concept here, this is called rationalizing the denominator. And to do that, you have to get rid of the I. You don't want that I. you want the I to go away out of the denominator. Now, if it's in the numerator, that's fine, but we have to get rid of it by making it a real number. And how do we do that? Well, we can convert this into 2i squared with a little 3i on top. But what is I squared again? It's -1. So I'm left with -2 on bottom, 3i on top. Might be better to write this as -3i over 2 as your final answer. You don't want any i's in the bottom, and you just get rid of it when there's only one term. You multiply by just I, and that's all you have to do. But what if there are two terms? We have 4 minus 2i over the quantity of 3 plus 2i. How do we get rid of the I in the second one? If we multiply by I, that's not going to work. So what we have to do is we have to multiply by the conjugate. Now, what is the conjugate? Basically, you just switch the sign of that second term, and you have to multiply it by on top and on bottom. So this one will take a little bit more work. When I FOIL on top, that's 4 times 3, which will give me 12. 4 times 2, that should give me minus 8i. Negative 2i times 3i, that should be minus 6i. Negative 2i times negative 2i should be plus 4i squared. Now, all of that is over. 3 times 3, when we FOIL, 3 times negative 2i, which is negative 6i. 2i times 3, which is plus 6i. Ooh, do you see that? Two things right there that'll cancel out. 2i times negative 2i. So that'll be negative 4i squared. Now let's look at this. This I squared can become a -1. I squared becomes -1. And when we rewrite this here, I'm going to be left with 12, and I'm going to combine, just for the sake of writing less, 8i and negative 6i minus 14i minus 4, because we made that I squared become a -1 and multiply times a 4, all over 9. Our 6 i's will cancel out, so we don't even have to worry about those anymore. Plus 4, because that -4 times -1 will give me a positive. So when I combine like terms, I'll be left with 8 minus 14i all over 13. That was a really bad box. Check out my other video on ACT problems with imaginary and complex numbers. Thanks for watching.